Have you ever downloaded an app, maybe on your phone, maybe your laptop, and then just realized it works? Like no installation headaches, no missing files popping up. It just runs. And then you kind of wonder how that exact same app can scale up, seamlessly to millions of users on some giant cloud server, often without a hitch. It's a bit like magic, right? Well, today we're pulling back the curtain on some of the fundamental technologies that make this happen. We're talking containers and virtual machines, VMs, and the really pivotal role of a platform called Docker. So, our mission for this deep dive, let's cut through the jargon, let's really understand what these things are, how they differ, and honestly, why getting your head around them is pretty crucial if you want to grasp modern software development, or even if you're just curious about how all this tech works behind the scenes. We're here to help you get a clear, thorough understanding pretty quickly, hopefully without the information overload, aiming for those real aha moments.
Exactly. And the source material we're drawing from for this deep dive, it gives us a really clear, structured way to compare them. We'll start with the basics, the definitions, then move through, how they're built differently, the architecture. Then performance, where you'd actually use them in the real world. And finally, a good look at Docker itself, because at its core, the big challenge these technologies solve is consistency. How do you make sure an application runs the same way, reliably, no matter where it is? Your laptop, a massive server, wherever. It's all about making it consistent.
Okay, right. Let's unpack that then. Containers. We hear that term a lot. What exactly is a container?
Yeah, good question. So um, fundamentally, a container is like a lightweight self-contained package. It bundles up an application, the code itself, sure, but also all its dependencies. We're talking libraries, configuration files, the runtime environment, basically everything that app needs to actually run. Think of it like a perfectly packed, standardized shipping crate, but for software.
Okay, a shipping crate for software. I like that.
And the real magic, the key benefit, is portability. Once you package that app in a container, it'll run exactly the same way everywhere. Doesn't matter what the underlying system is, as long as it supports containers. Now, this consistency comes largely because, unlike a full virtual machine, containers share the host operating system's kernel.
They share the kernel. Okay.
Yeah, imagine like a big apartment building. The building itself is the host OS kernel, providing the foundation, the core utilities. Containers are like individual apartments within that same building. They share the building's foundation. This makes them incredibly lightweight, often just megabytes in size,
Megabytes. Wow.
and lets them start almost instantly. No need to boot a whole OS. Plus, they're isolated from each other, so one container won't mess with another on the same system.
That shipping crate and apartment analogy, that really helps visualize it. Makes
Yeah.
sense. So if containers share the host OS kernel, like apartments in a building, what's a virtual machine then? How is that different?
Right, so what's fascinating is how VMs offer a different way to solve that same consistency problem. But they come with a different set of trade-offs. A VM is essentially an emulated computer system. It pretends to be a whole computer running on top of your physical hardware, the host. And unlike containers, each VM includes a full, complete operating system, Windows, Linux, whatever. Plus, it gets its own virtualized hardware. Virtual CPU, virtual memory, virtual storage.
A whole virtual computer inside the real one.
Exactly. And all this is managed by something called a hypervisor. Think of the hypervisor as a specialized manager or maybe a landlord for these virtual machines. Software like VMware or VirtualBox or Microsoft's Hyper-V, those are common hypervisors. They manage the VMs, allocate resources from the physical machine, and keep them separate.
Okay, so the hypervisor is the manager.
Yep. And the key features for VMs go first, complete isolation. Because each VM is a full OS, the boundary between them is really strong. Much stronger, generally, than between containers. They also offer amazing flexibility. You can run totally different operating systems side by side on the same physical machine. Windows and Linux, no problem. But the downside is they're more resource intensive. Running multiple full operating systems takes a lot more CPU, memory, and disk space. That's the overhead, and
Oh, no.
consequently, they're slower to start up. You have to boot an entire operating system each time, which can take minutes.
Okay, so, wow, quite different. On one side, these super lightweight, fast containers sharing the OS kernel, and on the other, these more heavyweight, fully isolated VMs, each with its own OS managed by a hypervisor. It sounds like they both solve that isolation problem, let you run apps separately, but the way they do it is totally different. So what does this all mean for someone trying to decide which approach to use? When would you pick one over the other?
That's exactly the right question. While both give you isolation and help with portability, those differences in architecture, performance, and how resource hungry they are, well, they're significant. Choosing the right one is really crucial. It impacts efficiency, how easily you can scale up or down, even security considerations. It really depends on your specific needs. It's definitely not a case of one being just better overall. It's about finding the right fit for the job at hand.
Right. Okay. Let's dive deeper into those architectural differences then, because you said this is where the performance and use case implications really stem from. So for containers, we've established they share the host OS kernel. That's the big one. Reduces overhead dramatically. They only bundle the application code and the specific bits it needs, libraries, config files, that sort of thing.
Precisely. Nothing more than necessary.
Which leads to that much smaller footprint, right? You said megabytes typically.
Yeah.
And they run as isolated processes managed by a container runtime engine.
Yep, just processes on the host, but walled off from each other.
Now contrast that with VMs. They include a full operating system, plus all that virtualized hardware. That means a much larger footprint. We're talking gigabytes often, right? Not megabytes.
Easily gigabytes, yes, because you have the entire OS image in there.
And they run as completely separate systems managed by that hypervisor layer.
Exactly. Separate machines, virtually speaking.
Okay, so if we connect that architecture directly to performance and efficiency.
Yeah, this is where containers really tend to shine for many modern uses.
Mm.
Because they share the kernel and have so little overhead, they start up incredibly fast, often in seconds.
Seconds versus minutes for a VM.
Right. And that low overhead also means much lower resource usage, less CPU, less RAM per application instance, which means you can pack way more containers onto a single physical host compared to VMs.
So essentially, more bang for your buck from your hardware. Run more apps on the same machine. That must translate into significant cost savings for businesses.
Absolutely. Huge cost savings potential. And this efficiency makes them absolutely ideal for modern approaches like microservices. You break a big application down into lots of small independent services that talk to each other.
Right, I've heard that term.
Containers make it super easy to deploy, manage, scale, and update each of those little services independently and quickly. It fits that model perfectly.
Okay, so containers are great for that microservices world. What about VMs then, performance-wise?
Well, VMs, with their slower startup minutes, remember, and higher resource demands, because each one needs its own OS and virtual hardware. They generally end up being better suited for, say, legacy applications that might have specific OS requirements, or situations where you absolutely need to run different operating system types on the same physical server, like that Windows app on a Linux host example.
Got it. So the performance trade-off is clear. Let's talk about real-world use cases then. Where do you actually see these things being used most often? What stands out to you?
For containers, definitely microservices like we just discussed. That's a huge one. They're also absolutely central to CI/CD pipelines.
CI/CD, continuous integration, continuous deployment.
Exactly. Those automated systems that help developers build, test, and release software updates much faster and more reliably. Containers provide the consistent environment needed for that whole process. And, naturally, they're a cornerstone of what we call cloud-native applications apps, designed from the ground up to run in the cloud, needing that scalability and portability across different cloud providers.
Okay, so modern development, cloud stuff, CI/CD, that's container territory. What about VMs? Where do they still rule?
VMs are still very common for running applications that require different operating systems on the same physical host. That flexibility is key. Think maybe running a specific Windows tool on your main Linux server farm, or vice versa. Also, really critical for older legacy applications, maybe apps that were built for, I don't know, Windows Server 2008 and depend heavily on that specific OS configuration. You can encapsulate that whole environment in a VM. And finally, in environments where you need really, really strong security isolation between different workloads, that full OS boundary in a VM provides a very robust separation.
Right, that makes sense. So there are definite trade-offs. You gain something, you give something up with each.
Absolutely. It raises that important question, what are the compromises? With containers, you get incredible speed, efficiency, density. But you are tied to the host OS kernel type. You generally can't run a Windows container on a Linux host directly, or vice versa, without extra layers. And while isolation is good, a severe vulnerability in that shared host kernel could, theoretically, pose a risk to all containers on it, although modern systems have strong safeguards.
Okay, potential security angle there, relying on the host kernel.
Potentially, yeah. Needs careful management. With VMs, you get that super strong isolation and the flexibility to run totally different OEs. But, as we've said, it comes at the cost of higher resource usage, more hardware needed, basically, and slower performance, especially startup times.
Okay, that lays out the landscape really well. Containers versus VMs, the pros and cons. Now, let's bring Docker fully into the picture. We've mentioned it, you said it popularized things. Where exactly does Docker fit into all this? It sounds like it was a real game changer.
Oh, absolutely a game changer. Docker is an open source platform. And what it did was it didn't just popularize containerization, it kind of.
Yeah.
It democratized it.
Yeah.
See, container technologies, things like Linux containers or LXC, they existed before Docker came along.
Right, you mentioned LXC.
Yeah, but they were often pretty complex to use, didn't have a great user experience, and lacked a sort of unified, easy-to-use ecosystem around them. Docker arrived and provided these really accessible, user-friendly tools. Tools to let pretty much anyone create, manage, and run containers easily. It just simplified the whole process immensely.
Democratized it. I like that.
Yeah,
So it made it accessible to everyone, not just hardcore system admins.
exactly. Developers, testers, operations folks.
Mm.
Suddenly, containerization was within reach for a much broader audience.
Okay, so how did Docker actually do that? What are the key pieces of Docker that made it work so well and, well, take over? Especially since container tech wasn't brand new.
Good question. You can think of the core Docker ecosystem as having maybe three main components, plus a central place to share things. First, you have Docker images. These are like the blueprints or templates. They're read-only and contain your application code plus all those dependencies we talked about. You build these images using a simple text file called a Docker file.
A Docker file, okay, like a recipe.
It's kind of like a recipe, yeah. Step-by-step instructions. Then, when you actually run that image, that blueprint, you get a Docker container. A container is a live running instance of an image. It's isolated, it runs your app. You can start, stop, delete containers. And managing all this building images, running containers, is the job of the Docker engine. That's the core software, the runtime that runs in the background on your host machine. It has a daemon, an API, and a command line interface, the CLI.
So engine runs things, images are blueprints, containers are the running apps. What was the sharing piece?
Oh, right. That's Docker Hub. Think of it like a cloud-based registry, kind of like GitHub for code, but this is for Docker images. It's a massive public library where people can upload their images, share them, or pull down images created by others. Like, need an official Python image, go to Docker Hub. Need a database, Docker Hub. This made distributing and collaborating on containerized applications incredibly easy.
Okay, so the engine, images, containers, and the hub for sharing. That makes sense. Why was that combination such a big deal, though? Why did it revolutionize things?
Well, several key reasons. First, sheer ease of use. Docker simplified what was previously complex. Simple commands like docker build, docker run, docker pull, docker push made creating, running, and sharing containers straightforward. Second, and maybe most importantly, it solved the infamous works on my machine problem.
Ah, yes. Every developer knows that one, but it works on my machine.
Exactly. Docker provided incredible portability because the container bundles everything the app needs, and Docker runs consistently across different environments: Linux, Windows, Mac, cloud. If it runs in a Docker container on your machine, it's almost guaranteed to run the same way in a container on your colleague's machine or on the production server. That consistency was a massive boost for collaboration and reliable deployment.
That alone sounds revolutionary for software teams.
It really was. Then Docker fostered this huge, robust ecosystem around it. It integrated beautifully with other tools. Things like Kubernetes, which is essential for managing large numbers of containers, what we call orchestration. Also CI/CD pipelines, like we mentioned earlier, and all the major cloud platforms, AWS, Azure, Google Cloud, they all embraced Docker support early on. And finally, Docker played a huge role in establishing open standards, like through the Open Container Initiative, OCI. This helped ensure compatibility and prevent vendor lock-in, driving really broad industry adoption.
Wow, okay. Ease of use, solved, works on my machine, built an ecosystem, and drove standards. That's
Yeah, the revolution.
So bringing it back to the practical comparison, how do we see Docker containers and VMs being used in the real world today, often side by side or replacing each other?
It's often a mix, depending on the need. Developers, for instance, heavily rely on Docker now. They use it constantly to create consistent development environments. Spin up a container with the exact database version, the right libraries, cuts down setup time massively, and ensures everyone on the team is working with the same setup as production.
Makes sense for developers. What about in production, running the actual applications for users?
In production, Docker containers, especially when managed by an orchestrator like Kubernetes, are the backbone for scaling microservices. Need to handle a sudden traffic spike? Just spin up more identical containers in seconds? That rapid scaling is a huge advantage. And again, that resource agency comes into play. Running multiple Docker containers on a single host is much cheaper than running multiple VMs, so organizations save significant money on hardware or cloud bills.
Right, the cost factor again. Speed, ease, consistency, cost, a lot of advantages. What about compatibility then? Are there still clear times when VMs are just the better or maybe the only choice?
Oh, absolutely. When you look at compatibility, Docker is fantastic, ideal even, for modern cloud-native applications designed for that kind of agility and scale. But VMs are still the go-to solution for legacy systems. Apps that need a specific, perhaps older operating system version to function correctly, you can encapsulate that whole old environment in a VM. Also, as we touched on, if you need that hardcore isolation provided by full hardware virtualization, maybe for extremely sensitive workloads, or if you fundamentally need to run different OS types, like Windows apps directly on Linux hardware, VMs are often necessary. In fact, it's quite common to see companies running Docker containers inside virtual machines.
How interesting. Kind of the best of both worlds.
Sort of. You use the VM layer for its strong OS-level isolation and maybe hardware management, and then within that isolated VM, you run containers for the application portability, density, and rapid deployment benefits.
Okay, that makes sense, using them together. Now,
Yeah.
you mentioned trade-offs earlier. No technology is perfect. Docker must have its limitations too, right? It can't be a silver bullet for everything.
Definitely not a silver bullet. It's important to have a balanced view. Docker absolutely has limitations. For one, there's a learning curve. While it's easier than older tech, you still need to understand the concepts, images, containers, volumes, networking. It takes some effort to get comfortable.
Right, it's not zero effort.
Not at all. Then there's the security aspect we touched on. Because containers share the host OS kernel, a severe vulnerability in that kernel could potentially affect all containers running on that host. Now, there are many layers of security and isolation built in namespaces, cgroups, security modules that mitigate this significantly, but it's architecturally different from the complete OS isolation of a VM. You need good security practices.
So security requires attention. Anything else?
Well, the main thing is Docker is fundamentally not a VM replacement across the board. It's just not suited for those use cases where you absolutely need full OS isolation, or if your primary goal is to run applications designed for a completely different operating system type than your host. That's really where VMs still hold their ground.
Okay, learning curve, shared kernel security considerations, and not a universal VM replacement. Got it. So after this really insightful deep dive, let's try and summarize. What does this all mean for you, the listener, trying to make sense of all this tech? What's the main takeaway?
Yeah, I think that the core message is pretty clear. Containers, largely powered and popularized by Docker, offer these really lightweight, portable, and incredibly scalable solutions. They are fantastic, almost purpose-built for modern cloud-native applications. Speed, efficiency, density. Virtual machines, on the other hand, provide that much stronger isolation and greater flexibility, especially when you're dealing with legacy systems or need to run diverse operating systems on the same hardware. They offer robustness and compatibility for those scenarios.
Containers for modern agility, VMs for legacy, and strong isolation.
Broadly, yes. And Docker's role in all this was absolutely central. It didn't invent containers, but it made them accessible, standardized them, and built the ecosystem that made them a cornerstone of today's cloud-native development. Yeah. Honestly, for anyone starting out in tech, or even just curious about how those seamless apps you use every day actually work behind the curtain, getting a handle on Docker is a really, really good starting point. It unlocks understanding of so much modern infrastructure.
That's a great summary. Containers, VMs, Docker, key pieces of the puzzle. So, to leave you with something to think about, as technology keeps racing forward and applications get even more distributed, running across even more places, how might the ongoing innovation we're seeing in both containerization and virtualization continue to reshape, maybe even blur the lines of what's possible in deploying software and optimizing how we use our computing resources? Something to maybe consider next time you update an app or hear about the latest cloud technology.